Hello everyone, my name is Jagan. I'm a PhD candidate from the University of Texas at Arlington. I welcome you all to the presentation of our work, Effectiveness of Dataset Reduction in Testing Machine Learning Algorithms. Today, this will be the outline of my presentation. I will start with an introduction and motivation to our work. Then I'll talk about the design of our experiments, followed with a discussion of the results. Finally, I'll be ending my presentation with the conclusion remarks and directions for our future work. From a software testing perspective, compared to traditional application, testing an application which uses machine learning algorithms can be expensive and time consuming. This is because ML algorithms or machine learning algorithms uses large volume of dataset as an input and discover insights and hidden patterns from those datasets. Because of this reason, each test case may have longer execution time, and hence the overall testing becomes expensive. As we can see, there is a need to speed up the testing process. One approach to address this problem is to replace the high volume test dataset with a smaller dataset, probably reduced using sampling techniques. This forms the motivation for our work. So, in this paper, our objective is to investigate the effectiveness of using a reduced dataset to test machine learning algorithms. That is, we explore via experiments, we evaluate how effective is to test machine learning algorithms using reduced datasets in comparison to the original datasets. Also, we also evaluate how do the two sampling strategies, that is random and stratified sampling strategies, compare to each other. In addition to this, we also explore in terms of testing machine learning algorithms, can branch coverage be used as a substitute for the mutation coverage? To perform our experiments, we use Weka as a subject program. As you may all know, Weka is a popular open source machine learning workbench. It consists of supervised and unsupervised learning algorithm implementation written in Java. For our work, we consider only the supervised learning algorithms, and among the different supervised learning algorithm implementations in Java, we use these four algorithms as our subject program: J48, Naivebase, AdaBoost, and Onar. The table below lists the Weka implementation details of these algorithms. Next, in terms of datasets, for large volume datasets to be used in our study, we use 5 datasets selected from Kaggle.com, an online data science community that maintains a repository of public datasets. Especially, all the 5 datasets used in our experiments are from different application domains. The table here in this slide indicates the meta information of the datasets used in our experiments. As you can see, we have 4 datasets that has binary class labels and 1 dataset which is by multi-class label dataset. In terms of number of attributes, we have a dataset supply chain with low as 5 attributes to a dataset video game dataset which has 56 attributes. And in terms of number of instances, the lowest among the number of, or the least among the number of instances is the Australian weather datasets with 142,193 instances, the most being the video games dataset with 999,999 instances. To, to conduct our study, recall that the main objective of our study is to compare how uh, can, can we replace original datasets with reduced datasets to test machine learning algorithms. To do that, we need to generate the reduced datasets. In our experiments, we for each of the 5 original datasets, we generate 2 group of reduced datasets using Baker's pre-processing filter. Group 1 consists of reduced datasets generated using random sampling, and group 2 consists of reduced datasets using stratified sampling. The only difference between random and stratified sampling is that datasets reduced using stratified sampling will maintain the class distribution of the original dataset, whereas datasets reduced via random sampling may or may not maintain the original class distribution. So in each group, we generate reduced datasets in 4 different sample sizes. We generate a reduced dataset of size 100 instances, 200 instances, 400 instances, and 800 instances. In addition to that, to reduce variations in sampling, for each sample size, we generate 5 samples with different random seeds. So in total, for a data set, we will have 20 samples generated using random sampling and an additional 20 samples generated using stratified sampling. So overall, for a given data set, we will have 40 samples from 2 groups. Once we have the reduced data sets, to perform our experiments, to measure the test effectiveness of testing machine learning algorithms, we use branch coverage and mutation coverage as a metric. As you all know, Jacoco is a open source free code library for Java that can be used to measure the branch coverage. And to measure the mutation coverage, we use the mutation testing tool called PitTest developed by Mr. Henry Coles. To measure the branch coverage, we execute each dataset with Baker's default configuration options, and the execution is recorded using Jacoco. The output from this execution is stored in a text file, which is later used during our mutation coverage experiments. To perform mutation testing, we use JUnit test and the PitTest framework, and we compare the expected output of the original program execution against the output of each mutated version. This will be discussed later. We will discuss the coverage results. First, we will discuss the branch coverage results of the original datasets. Then we will discuss the branch coverage results of the reduced datasets, followed by the discussion of the mutation coverage results. Next, we discuss the branch coverage results of the original datasets. For each of the 5 algorithms, we execute the original datasets with Baker's default configuration options. The results indicate that supply chain dataset consistently achieve higher branch coverage across algorithms. Let's consider the case of ONAR algorithm for discussion purpose. Here, supply chain datasets covers 51 branches out of the total 88 branches. Compared to this, Australian weather dataset covers a significantly lower number of branches. It covers a minimum of it's meager of 17 branches out of the total number of 88 branches. On further inspection, we found out that the attributes data type shall contribute to the overall branch coverage. That is, supply chain dataset consists of attributes that belong to numeric data type as well as some other attributes that belong to the nominal data type. Whereas Australian weather, in the case of Australian weather datasets, all the attributes belong to the nominal data type, and hence the methods and branches dealing with the numeric data types was missed. In the case of ONR algorithm, a method named as new numeric rule with 36 branches was missed while executing the algorithm with Australian weather dataset. Also, in addition to this, we'd also like to point out that of the total of 88 branches, supply chain datasets executes 51 branches and it misses out on 37 branches. This can be explained uh, by the way we execute our experiments. That is, in our experiments, we execute each algorithm with Wacker's default configuration options, and the dataset used in our experiments are clean and does not contain any missing values, and hence branches related to error handling and other configuration options were missed. Finally, I'd like to point out that although the overall branch coverage appears to be lower, this does not affect our conclusion. The reason being, the main motivation for our work is to compare the branch coverage achieved by the original datasets with that of the reduced datasets. In a sense, the branch coverage of the original datasets act as a baseline to compare with the branch coverage achieved by the reduced dataset. Next, we discuss the branch coverage results of the reduced datasets. Moving on, let's discuss the branch coverage results of the reduced datasets, and let's see how they fare up with the branch coverage results of the original datasets. The table on the left presents the branch coverage results of the reduced datasets produced via random sampling, and the table on the right presents the branch coverage results, relative branch coverage results of the reduced datasets produced via stratified sampling. If you recall, for each dataset, we created reduced datasets in 4 different sizes with 100 instances, 200, 400, and 800 instances. And for each size, we created 5 samples. So in this table, we present the median branch coverage achieved by each size relative to their baseline branch coverage. That is, consider the case of reduced datasets of forest cover with J48 algorithm. A value of 1 over here indicates that reduced versions of the forest cover dataset on executing with J48 algorithm achieves a branch coverage that is identical to its baseline, which is identical to the branch coverage achieved by the original dataset. Now, let's compare the branch coverages achieved by reduced datasets of size 800 instances. As you can notice, predominantly all the across algorithms, the reduced versions can achieve and branch coverage that is either identical or closer to their respective baseline branch coverage. In fact, 39 of the 50 reduced datasets of size 800 instances produced by both random and stratified sampling achieve branch coverage that's identical to their corresponding baseline. branch coverages. So, since majority of the reduced data sets across algorithms can achieve a baseline closer to identical to their original data sets, we do not consider uh, consider sample size that's larger than 800 instances. Uh, Now, next, let's discuss on on for each algorithm. In the case of J48 algorithm, as you can notice, reduced data sets of forest cover, supply chain, and video games can retain their baseline coverage with 800 instances. In the case of naive-Bayes algorithm, uh, all reduced data sets of all sizes can achieve and branch coverage that is identical to its baseline, and in some cases a bit higher than its baseline. For the remaining three algorithms, that is AdaBoost, decision stump, and ONR, in most cases, that is apart from crime dataset, all reduced version of all the remaining four datasets achieves branch coverage that is either identical to its baseline or closer to its baseline. If you notice across crime dataset, the reduced versions of the crime dataset appears to have a significant drop in coverage for certain algorithms such as J48, AdaBoost, and ONR. Consider a case of reduced versions of crime dataset on J48 algorithm. We noticed that the reason for a significant drop in branch coverage for the reduced versions of the crime dataset can be attributed to the lack of class label representativeness, or in other words, a class imbalance problem. If you recall, among the 5 datasets, crime dataset has around 284,807 instances. However, 99.82% of these instances belong to class label 0, and only 0.18% of these instances belong to class label 1. So, on drawing 100 instances at random, all the 100 instances belongs to one class, which is in this case class 0, and hence most most of the branches were missed due to lack of class label representativeness. We confirmed this by comparing the results of crime datasets on J48 with size 100 instances and 200 instances. If you notice, a size 200 instance achieves and a median relative branch coverage of 0.12 versus size 200 instances achieves a relative median branch coverage of 0.35. This is because all the 5 samples for size 100 instances have instances belonging to only one class, whereas 3 out of 5 samples for 200 instances have representation from both the classes. Hence, there is a increase in branch coverage. Due to this class imbalance problem, reduced versions of the crime dataset seems to suffer from loss in branch coverage. Next, let's compare the coverage results achieved by reduced datasets of random sampling versus reduced datasets of stratified sampling. As our results indicate, in most cases, dataset reduced using both approaches are identical to each other. That is, they achieve the same branch coverage. In the case of, consider the case of Australian weather, supply chain, and video games. These 3 datasets, in addition to that forest cover, these 4 datasets has a relatively very good class representation in their original dataset. Hence, the reduced versions of these datasets also achieves a branch coverage that is closer or identical to their baseline. However, compare this to that of the crime dataset. When in the case of stratified sampling, in the a reduced versions of crime dataset of size 100, 200, and 400 instances performs very poorly compared to a size of 800 instances. This is because uh, of the nature. This is because the way samples are drawn in stratified sampling. We call that in stratified sampling, the reduced datasets maintains the original class distribution of the instances. So, uh, given the given the fact that 99.82% of the class instances, given the fact that 99.82% of the instances in the crime dataset belongs to class 0 and only 0.18% of the uh, instances belong to class 1. When you draw 100, 200, or 400 instances via stratified sampling, all the classes belong to class 0, and hence there is a huge reduction or decrease in coverage, I should say. Uh, to for this scenario, that is for crime dataset with 284,807 instances, to generate a reduced dataset from using stratified sampling, we need at least 556 instances to enable or to ensure uh, um, uh, that the reduced dataset has representation from both the class labels. This is again reflected in the ONR algorithm as well. If you notice here, until the size is increased to 800, there seems to be a reduction in branch coverage. Overall, among these two sampling approaches, the results indicate in most cases around 75% reduced datasets generated using both random and stratified sampling exhibit identical behavior. Also, 80% of the overall reduced datasets achieve branch coverage that's either identical or closer to the baseline. This means that the volume of a dataset does not directly uh, attribute to the branch coverage. So the results suggest that in most cases, we will be reduced datasets can be used in place of the original dataset to speed up the testing process. However, if a tester decides to use a stratified sampling approach to generate reduced dataset, the tester should choose the size of the reduced dataset based on the original class distribution, such that each class label will be represented in the reduced dataset. To summarize, the volume of a dataset does not directly attribute to the branch coverage. So the results suggest that we can use reduced datasets to speed up the testing process. Rather, factors such as a lack of class representativeness in a reduced dataset could impact the branch coverage. Moving on. Next, we will quickly discuss the mutation coverage results of the reduced dataset. Let's discuss the mutation coverage results. In our experiments, we use PIT test, a widely used mutation testing framework, to measure the mutation coverage. PIT can automatically seed one fault at a time into the subject programs and execute the mutated code against a specified unit test. So in our experiments, we executed each datasets, be it original or the reduced ones, with Weka's default configuration options, and their output is saved in a text file. Later, the output of the original version of the program is compared against the mutated version of the program, and if both of these output differs, then the mutant is considered to be be killed. Else, the mutant is considered to be a surviving mutant. The mutation coverage is measured as a ratio of total number of killed mutants over total number of mutants in the introduced in the program. So let's look into the mutation coverage results presented in this slide. On the left, you see the relative mutation coverage of the reduced datasets produced by a random sampling, and on the right, you see the relative mutation coverage of the reduced dataset produced using stratified sampling. Similar to branch coverage results of the reduced datasets, the numbers presented over here represents a relative mutation coverage. That is, a value of 1 indicates the reduced version of a dataset achieves a mutation coverage that is identical to the mutation coverage achieved by its original dataset. So, if you compare the reduced datasets of size 800 instances, in most cases, across random and stratified sampling, mutation testing with reduced dataset of size 800 instances can achieve an mutation coverage that is either identical or closer to its baseline. To summarize, the reduced datasets can retain the mutation coverage achieved by the original datasets, and majority of the mutation coverage results mirrors with their respective branch coverage results. Consider the correlation graph shown over here. On the left, you see the correlation graph between the relative branch coverage and relative mutation coverage of reduced datasets produced by a random sampling. And on the right, you see the correlation graph between the relative mutation and branch coverage for reduced datasets produced by a stratified sampling. Both these correlation graphs indicates a strong positive correlation, with the graph on the left having a strong with a graph on the left having a Pearson coefficient of 0.94 and graph on the right having a Pearson coefficient of positive 0.93. So we can say from these results, we can say that the in most cases the branch and mutation coverage correlates well. To summarize, we investigate the use of reduced datasets in testing machine learning algorithms. We use 4 supervised learning algorithms from Veka as our subject programs and 5 datasets from kaggle.com to perform our experiments. We compare the branch and mutation coverage achieved by the original datasets with the reduced datasets generated using 2 sampling strategies, namely random and stratified sampling. Our results indicates in most cases the reduced datasets of very small sizes can retain the branch and mutation coverage achieved by the original datasets. That is, in most cases, reduced datasets can be used to effectively test machine learning algorithms, thus speeding up the testing process. Also, our results also indicate that the coverage results of the reduced datasets generated by 2 sampling strategies are very similar. In fact, 628 of the 800 reduced datasets produced by the 2 sampling strategies achieve the same coverage. Finally, we also noticed that the branch coverage correlates well with the mutation coverage. Work. We plan to investigate the reduction of larger multi-level datasets and their effect on testing machine learning algorithms. Also, we also plan to extend this work in testing unsupervised learning algorithms. Compared to supervised learning algorithms, the unsupervised learning algorithms learn from an unlabeled datasets, and thus it could be harder to validate its output. We also plan to develop new methods for dataset detection that can be used to test machine learning algorithms. Thank you.